welcome to part 2 of the chapter 5 day 6 notes. We're going to pick up with example number 4. So let's take a look and see what it says. The graph of f of t is shown. If capital F of x, which is the antiderivative of f of x, is equal to the integral from 0 to x of f of t dt, then we want to fill in the values for the antiderivative of f of x in the table below, and then sketch a possible graph for f of x. All right, so if we're going to take a look at this, so this graph over here is f of t. So, you know, whenever you're looking at graphs, you want to make sure it's labeled and you know what you're looking at. So that's f of t. So we know that the antiderivative of f is the integral from 0 to x of f of t. So if we wanted to find the antiderivative of f of 0, then we are going to take the integral from 0 to 0 of f of t dt. Well, because that interval has no width, the integral is 0. So that's going to equal 0. If we go to find the antiderivative of f of 1, all right, which is the next value in the table, then that means that we want to take the integral from 0 to 1 of f of t dt. In this situation, to do that, we are going to need to basically find the area under the curve from 0 to 1. So that's going to be this triangle right there. So that area is going to be 1/2, the base is 1, and the height is 2. So 1/2 of 1 plus 2 is going to equal 1. So now we know that f of 1 is 1. All right, now the next integral, or the next value that we're going to take a look at, is from, we want to find the antiderivative of f of 2, which is the integral from 0 to 2 of f of t dt. All right, now that's one way to think about it. Another way to think about it is it's going to be the integral from 0 to 1 of f of t dt plus the integral from 1 to 2 of f of t dt. Now, the reason why writing it like that is helpful is because we already know what the value is from 0 to 1. So that's 1. Now we need to add, let me just kind of write that up here. So that's 1. Now we need to add the integral from 1 to 2. So the integral from 1 to 2 would be represented by that rectangle right there. And the area of a rectangle is base times height. So 1 times 2. And 1 plus 2 is 3. So in this case, we can, because we're finding previous integrals, we can use those to help us come up with these values a little bit easier. All right. So now if you go ahead and you take a look at the next one, right, we want the integral from 0 to 3 of f of t dt. So we already know the integral from 0 to 2 is 3. So what we can do is we can call this 3 plus the integral from 2 to 3 of f of t dt. All right, and hopefully you guys are starting to see the pattern and get the picture here. So now we want to add this area, which is another triangle. All right, so the area of that triangle is going to be 1/2. The base is 1. The height is 2. So that's 1. So 3 plus 1 is 4. So the integral from 0 to 3 is going to be 4. All right, and now we're going to basically continue along with that idea. All right, so for the next one, antiderivative of f of 4 is the integral from, trying to pick a different color, is the integral from 0 to 4 of f of t dt. All right, which again, you could think of that as 4 plus the integral from 3 to 4 of f of t dt. So now when we go and we find that integral from 3 to 4, we're looking at this triangle right here. So a couple things are going to come into play. One, it's below the x-axis, so we have to know it's negative. So I'm going to end up subtracting whatever that area is. It's a triangle, so we have half of the base, which is 1, and the height, which is 2. So 4, minus 1 in that case is 3. So we get a value of 3 again. All right, and again, keep this up. We're going to do the integral from 0 to 5 of f of t dt. So we can take that 3 value that we got before and essentially add the integral from 4 to 5 of f of t dt. So that's going to be 3. All right, well, when you look at from 4 to 5, there you go. You have a rectangle that's below the x-axis, so it's negative, so we're going to subtract. The base is 1, the height is 2. So 3 minus 2 is 1. And finally, we need the integral from 0 to 6 of f of t dt, which we can use our 1 that we got before, and we can add the integral from 5 to 6 of f of t dt. So we've got 1, and in this case we're going to add, or no, sorry, we're not going to add, because now from 5 to 6 we have this trapezoid. All right, so it's below the x-axis, so we're going to go ahead and subtract 1/2. We need the height and then the sum of the bases. So the bases are the parallel sides, which are this height here, which is 2, this height here, which is 1, so that's going to be 2 plus 1. And the height of the trapezoid is the distance between those two bases, so from 5 to 6, which is 1. So when we simplify that all down, we've got, let's see, 2 plus 1 is 3. 3 times 1/2 is 3/2. So 1 minus 3/2 is going to be negative 1/2. All right. And what that does is that gives us values for the antiderivative of f at certain points. We could then go ahead and plot those points to come up with a possible graph, because it wants us to sketch a possible graph for the antiderivative of f of x. So antiderivative of f of 0 is 0, so we're going to have a point here. All right, then we're going to have the point 1, 1, so we have a point here. We have the point 2, 3, so we have a point here. The next point is 3, 4, so we're 3, 4. The next point is 4, 3, so we're over 4 up 3. Our next point is 5, 1, so we're over 5 up 1. And our final point is going to be 6, negative 1/2, so over 6 down 1/2, which is going to put us down here. And now, we don't know exactly what the shape of the graph looks like. It's most likely not going to be straight segments connecting all the points. So there's probably going to be a shape that resembles something along those lines, like that. And that is how you could come up with the graph for the antiderivative of f. All right. So knowing that the antiderivative of f is the integral of some function, and we have the graph of the function, that's one way to come up with that graph. All right. We're going to go ahead, guys, and take a look at the next examples on the next page. All right, so in example 5, it says we want to evaluate the integral from 2 to 4 of the expression of the quantity 6 plus 2x minus x cubed using the following values. So what we want to look at is we've got certain integrals given. So the integral from 2 to 4 of x cubed is 60. The integral from 2 to 4 of x dx is 6. And then the integral from 2 to 4 of dx is 2. So what we want to do is we're going to go ahead and break this integral up into its parts. So we could have the integral from 2 to 4 of 6 dx plus the integral from 2 to 4 of 2x dx minus the integral from 2 to 4 of x cubed dx. Now, one of the things you'll notice is we don't have 6 dx here. So what you can always do with integrals is pull out the constant. So I can think of this as 6 times the integral from 2 to 4 of dx. This one, again, has a 2x. We only have the integral of x. So the 2 can pull out in front, and it's 2 times the integral from 2 to 4 of x dx. And then this one is something that we know, so we're going to go ahead and leave that as the integral from 2 to 4 of x cubed dx. From there, we can simply substitute. So this is 6 times. Well, the integral from 2 to 4 of dx is 2. So 6 times 2 plus 2 times the integral from 2 to 4 of x dx is 6. And then, whoops, that's supposed to be a minus. And the integral from 2 to 4 of x cubed is 60. So if we combine like terms, 6 times 2 is 12. 2 times 6 is 12 minus 60. So 24 minus 60 is negative 36. So therefore, the integral from 2 to 4 of 6 plus 2x minus x cubed is negative 36. All right, we're going to go ahead and take a look at the next example here real quick. Example 6 says, given that the integral from negative 1 to 3 of f of x dx is 8, we want to find the integral from negative 1 to 3 of f of x plus 5. So the quantity f of x plus 5 dx. Pause the video, try it on your own, see what you come up with. All right, so the first thing I'm going to do in this situation is I'm going to rewrite this as the integral from negative 1 to 3 of f of x dx, and then that's going to become plus the integral from negative 1 to 3 of 5 dx. So what we know is, based on the given information, is this integral right here is 8. All right, this is where we need to be careful. So one way to do this would be to just evaluate this integral. If we want to take the integral from negative 1 to 3 of 5, we can take the integral of 5, which is 5x, and evaluate it from negative 1 to 3. So we get 8 plus, and then we're going to evaluate this, so we're going to do 5 times 3 minus 5 times negative 1. And if we simplify that, we get 8 plus 15 plus 5, which is 20, which is 28. All right. Now, again, that's one way to do this. Something that you might start to pick up on is when you take the integral of a constant, all right, when you take the integral of a constant, you can always find that integral by multiplying the constant by the width of the interval, all right? And the reason that works is, if you were to think kind of graphically, I'll do this off to the side here real quick. If we have the function 5, all right, the function 5 is some horizontal line at 5. And if we want to take the integral from, negative 1 to 3, basically what we're talking about, the integral from negative 1 to 3, is the area of this rectangle. And that's what we're finding when we take the integral of a constant, is we're finding the area of some rectangle. The constant is the height of the function, which is 5, and then the interval from negative 1 to 3, that gives you the base of the rectangle, and from negative 1 to 3 is 4. So just something to think about conceptually as you look at these, and might help you better understand why the integral from negative 1 to 3 of 5 is 20. All right, guys, that does it for part 2 of the Chapter 5, Day 6 notes. Make sure you check out part 3.